Today, we're jumping into something that sounds straight out of science fiction, teaching an AI how to design the perfect computer chip. Now, the potential here is absolutely massive, but there's one really big hurdle we have to get over first.
I mean, seriously, think about that for a second. The brains inside your phone, your computer, the chips running the entire internet. What if all of them could be designed by an AI? It sounds a little crazy, but we're pretty much there.
But, and this is a huge but, there's a catch. The AI, as brilliant as it is, has this little habit of, well, making things up. It hallucinates. And when you're crafting a physical microchip, one tiny mistake isn't just a bug, it's a disaster. So the real question is, how do we get all that AI brilliance without the fatal flaw? To really get why this new solution is so clever, we first have to understand why designing chips has always been such a massive pain. You know, the old school human-powered way. This right here is the heart of the problem. If you're writing software and you find a bug, no big deal. You just push an update, right? It's fixable. But a computer chip? That's hardware. It's physically etched into silicone. It is literally set in stone. If you mess up, that mistake is permanent, and you might have to throw away millions of dollars worth of product. The stakes are incredibly high.
So for decades, this has meant that brilliant engineers spend countless hours manually writing the blueprints for these chips, using something called a hardware description language, or HDL. It's slow, it's painstaking, and it is wildly expensive, all because every single detail has to be perfect. So naturally, people thought, there has to be a better way. Let's automate this. And that led to a couple of different approaches for getting machines to write this code. Let's see how they compare. Okay, so first up is a method called high-level synthesis, or HLS. And just look at the code it spits out. It's a dense, chaotic-looking mess. It might work, but good luck trying to figure out what's going on in there if you're a human. And that's the story of HLS. It does get the job done. It creates a design that is functionally correct. But the code is just clunky. And the chips it designs are often bigger and more power-hungry than they need to be. It's reliable, sure, but it's not elegant at all. Now get ready for a big contrast. Here's code for the exact same chip, but this time written by a large language model, an LLM. See the difference? It's clean, it's organized. It honestly looks like something an expert human engineer would have written. The promise here is just incredible. LLMs can create these beautiful designs that are not just easy to read, but could also be way more efficient. Smaller, less power, the whole deal. But like we said at the start, there is a very, very big catch. And that catch has a name that's become pretty infamous in the AI world, the hallucination problem. This is the one thing standing in the way of just letting AIs design all of our hardware. Now, when an LLM hallucinates in this context, it's not just making a small typo. It's inventing a piece of logic that is fundamentally broken. It might completely misunderstand an instruction and just make something up that doesn't work. For a chip, that kind of functional error means the entire design is totally useless. So, just how big of a deal is this? Well, think about it like this. Without a guiding hand, a significant number of the designs an LLM creates, almost 30% in some cases, have these critical functional errors. They just flat out don't work. That's a huge failure rate you have to fix. So what do you do if you have a brilliant student who's creative and fast but just gets the answer wrong sometimes? Well, you get them a teacher. And that is the simple, genius idea behind a new system called CorrectHDL. Okay, so here's how this awesome process works. First, you have the LLM student write its elegant, efficient code. At the exact same time, you have the HLS teacher create its own clunky but guaranteed to be correct version. Then, you test them both. If the student's answer doesn't perfectly match the teacher's, the system points out the exact mistake to the LLM and says, try again. It's this amazing feedback loop. That perfect version from the HLS tool has a special name. It's the golden reference. You can think of it as the teacher's answer key. It's the undisputed, 100% correct source of truth. It might not be the best design, but you know its behavior is perfect, which makes it the ideal yardstick for checking the LLM's homework. So what happens when you pair the creativity of a brilliant LLM with the strict, no-nonsense correctness of an HLS teacher? Well, you get the best of both worlds. And the results? They're pretty mind-blowing. First things first, does it actually work? Look at this. Left to its own devices, the LLM passes the test less than a third of the time.
But with the correct HDL teacher guiding it, boom, the pass rate more than doubles to nearly 70%. That is a gigantic leap in reliability.
But it's not just about being correct, it's about being better. This chart shows the actual physical size of the chip. The correct HDL designs, the ones made by the student with the teacher's help, are on average almost 25% smaller. And in the world of chip making, smaller is everything. It's cheaper and more efficient. And for the trifecta, check out power consumption. The correct HDL designs use almost 27% less power. That's a massive deal. That translates directly to longer battery life on your phone and lower electricity bills for giant data centers. It's a huge win. So let's wrap this all up. By giving the AI a teacher, we get chip designs that are functionally correct, way more efficient in size and power, and are still clean enough for a human to read and understand. We're talking about a quality of work that rivals and sometimes even beats what human experts can do. And this all leads to one last, really exciting thought. This whole student-teacher model, it's not just for making computer chips. This could be a blueprint for using AI in any field where the stakes are incredibly high and mistakes just aren't an option. Think medicine or structural engineering. If an AI with a perfect reference can master something this complex, what expert field is next?